Hello and welcome to our next talk. If you ever wondered how long it would take you to build your own rocket, this is the talk for you. Let our experts, Tom, Luca, Reinhard, Tobias Jäger, Adrian Leutner and Vincent Preuss invite you to their journey and see how they are building their rocket in just 1 year. Their team, Elara Aerospace, is on an historic journey to be the first student team to launch a methalox rocket beyond 100 kilometers. Tom Luca Reinhardt is CEO and founder of Elara Aerospace, studying aeronautical and astronautical engineering at the University of Applied Sciences in Munich, and a former board member of TUM Boring Innovation in Tunneling EV. Adrian Leutner, after his standout achievement as a technical co-lead at TUM Boring, he is now CTO and technical lead at Elara Aerospace. When he's not building a rocket, he is sharpening his project management skills as an executive assistant to the CEO at a factoring company. Tobias Jäger is head of strategy at Elara Aerospace and is currently pursuing a master's in medical technology at TUM. He spent 2 years as a board member and project lead at TUM Boring. And finally, Vincent Preuss just finished his Abitur and will soon continue studying management and technology at the TUM Munich. After several internships at various sales departments and also gathering experience as former sponsoring and marketing lead at TUM Boring, he is now the sponsoring lead and head of sales at Elara Aerospace. And with that, I guess it's time for rocket science.
Good morning, everyone. Let's see if our slides start. There we go. So welcome to How to Build a Rocket in Just 1 Year. And welcome to the lecture of Rocket Science 101. Why do we want to do this goal? How do we build a rocket in 1 year? And what does it take to build a rocket in 1 year? Why do we want to build a rocket in 1 year? The simple answer is we want to launch one of the biggest student rockets, or at the end it will be the heaviest student rocket ever, into suborbital space. It has never been done before that a student had launched a rocket in 1 year, or a commercial company launching a rocket in less than 5 years. Even the biggest or most renowned rocket, Falcon 9, took 5 years in development, and we're trying to beat those in development times. It all started with a dream of building rockets and understanding how it works. You have blueprints that look like this from all over the world. This is now a Russian rocket, but it's the dream of probably every student of aerospace to understand how those work and what all the little parts do. And that's what fascinated me about aerospace and rocketry, especially trying to understand what all these pipes do in a rocket engine. Technically, it's fuel and an oxidizer that you mix, combust, and that's it. But there's a lot more to it, and Adrian will probably answer a lot of those questions later, how we try and simplify that design so that we can actually do it in a lot less parts and simpler than what we see in front of you here. For that, we need a great team. We have a team of around 20 students working on this project whilst also studying. We have 4 of us right here. We are kind of the core team behind it, and most of them I've met in a previous project called TUM Boring. We won the Elon Musk Not a Boring competition in 2023, and with our knowledge in TBMs and team building, we founded this project, Elara Aerospace. Everyone has their unique skills, some more in the office, like Tobias Jäger, some more in the hardware, as Adrian Leutner, or me and Vincent going to events and collecting sponsors for our previous projects and the upcoming ones. Why do we want to have another team here in Munich? We think it's very important for students breaking records. We've got the time, we have the resources, and with that we want to break world records around the world. There are hundreds of teams taking part in competitions, but we don't think that's the right place for us. We have our expertise in breaking records with our TBM reaching 11 millimeters a second of advancement speeds, which is something that no other team achieved during that competition. And with our first rocket, we don't only want to break 1 world record, it's a total of 3. We will have the worldwide biggest electric pump-fed rocket engine that Adrian will talk more about later. We'll have the heaviest rocket ever built at 1 metric ton. It's heavier than any student has built at this point. And We'll be breaking the height record that is currently held by a US team, which is just over 100 kilometers. We aim for at least 130 kilometers with our rocket capable reaching more than that easily. So we have enough velocity to even reach 400 kilometers, which might become an issue if we go that high. We don't want to hit the ISS. What makes us different? We put a lot of effort into optimizing our design for additive manufacturing. So we try and use additive manufacturing wherever it's possible. We kind of use the philosophy that Elon Musk presents at SpaceX and Tesla, which is the best part is no part. We'll also put a lot of focus on reusability. So the launch vehicle that we're building doesn't only launch once, but multiple times. So we already schedule a launch for a couple months after the first launch happens. So we'll have parallel development, similar to how SpaceX is building Starship right now in Boca Chica. For that, we will be recovering the first booster, someone like this, maybe not the same scale. Ours is just 10 meters long, but we will be towing it back with the Coast Guard back to land and then trying refurbishing it and launching it again. With the second flight, we already want to prove technologies such as relighting engines, not for landing, but just to demonstrate the technology and that we're able to do those kind of things. So during our descent for the first flight, or for the second flight, we will relight the engines, demonstrate the possibility of a student-built rocket engine doing that, and then we will let it glide to the ground with a parachute again. And all of that is with the goal of actually launching a rocket not once, but multiple times a year, with the goal of launching over one time a month, allowing students worldwide to launch payloads to suborbital space and test their technologies that they are developing at different universities worldwide, all at a most cost-effective point where they can afford it themselves. That's one of the biggest hurdles that students have, that they can't afford doing a rideshare mission with SpaceX unless it's government funded, and that's where we want to allow them to kind of have that possibility as well. This is our launch site. We partnered with a company that's building those launch sites. We will go and visit this launch site in the next coming weeks, hopefully end of July, and make sure that the launch site is suitable for our first launches. We are able to launch suborbital rockets from this site, which is the most important component, but we also want to partner with this company to make sure that we can have orbital flights in the near future that our team will talk about later as well as a long-term goal. The whole flight will start on Sardinia. We'll have our burnout at around 20 kilometers, coast to our 130 kilometer apogee, and then we'll use our reaction control system to reorientate our rocket and get our rocket ready for re-entry, where we'll then deploy our parachute a couple kilometers above ground and then do a soft splashdown just off the coast of Sardinia, hopefully not on Italy. That will not be that ideal. And with that, we'll go over to the technical part, where I'll hand you over to Adrian Leutner.
Thank you very much, Tom Luca, for presenting. I will today explain you the insights of the rocket, at least a little bit, giving you the insights. How big is our rocket? It's 10 meters in height. It's half a meter in diameter. So it's already quite big, one ton. And yeah, the payload that we can additionally take with us is at this point 50 kilograms. So if you have any ideas what we should take, please feel free to ask us afterwards. Yeah, coming to the rocket. So the rocket, at the front, you see the payload and avionics bay. So inside here we have a lot of electronics and whatever you want. Then we have our parachute bay. So here the parachute will come out. Then we have a composite overwrapped pressure vessel. So this is basically, it's a helium tank. I'll explain it later. And then you see our reaction control system, RCS. This is a system that makes sure that the rocket is really stable in flight, so it prevents it from turning around. And also in the future, it helps us to do a self-propulsion landing, like Tom Luca mentioned. Then we have the tanks, which is quite a lot of the rockets, so around 700 kilograms. So makes out a lot. And then the heart of the rocket, the aft section, there we have the rocket engine. And yeah, I'll go into that. Here you see the rocket engine. So if you are familiar with rocket engines, most of them are bell nozzles. In this case, we are also using a bell nozzle. There are some issues with rocket engines. So if you don't cool them, they start to burn. And that's why you need very cold propellant. In our case, Tom Luca mentioned we are using methane, liquid methane and liquid oxygen. And you can see it here at the bottom. There we will push down the liquid oxygen at around minus 180 degree, coming there with 120 bar of pressure inside. And here on the right side you see our regenerative cooling, so cooling channels that swirl around. And inside here it's around 3,500 degree Kelvin. So if we wouldn't have it, it will burn. And then at the end, in the top, there both the propellant and the oxidizer come together, get injected. Yeah, what makes it possible to build it as a student team? First of all, it's actually technology, since we have the capability of using 3D printers. If you think of being back in the days, this was really, really hard to build a rocket engine. It was really, really hard, and this is actually making it possible for us to do it in that time and in general. Yeah, and as Tom Luca mentioned, it's electric turbopump fed, so the pressure that we generate in there, so it's meant to have around 50 bar in there, is coming from kind of electric pumps. And I'll show you the injector plate right now. So here, it's just the part you saw in the front of the engine. We have 42 coaxial swirl injectors, so maybe you remember it from your garden. If you have a garden, you have water out there and you open the valve and it's like spraying funny out. That's actually what those injectors are doing. And yeah, in the middle we have our ignition system, so to be capable of reigniting the whole engine again. And yeah, that's a future thing. But first of all, we want to, so you can think of it like a big lighter, a big lighter. And yeah, this is also 3D printed. This is also here, a small look at our tanks. So Toby will later talk about that. So we decided to be very quick, and in terms of being quick, we need to simplify a lot of parts. So first of all, we thought, hey, we do everything out of carbon, but there's a lot of stuff which is hard to make it tight and so on. And in order to achieve the rocket start in 1 year, we decided on really simplifying it. So in this case, we are using Type 1 tanks. This means this is really a metal tank and nothing special like you normally know. Yeah, then on the right side, you see the composite overwrapped pressure vessel, the helium tank. So this tank we need in order to make sure that the tanks here with LNG and oxygen are not imploding. Because when we start the engine and all the propellant is flowing out, normally they would implode if we wouldn't fill it. So this makes sure that we maintain 7 bar of pressure inside. So really making sure everything works out. Then here, this is the part where you can think of, maybe as a company, whatever, if you have an experiment, that is the area where you can put in your stuff. As a reference, you can see a basketball, maybe to get a feeling how big it is, how much space we have. Yeah, and in general, the question arises, I think, how are we doing it? How do we do it as students? We want to build a rocket, that's for sure. And what do you need to build a rocket? yeah, you need you need rocket engineers. But since all of our students, most of them, never built a rocket, how to do it? And I'll explain it to you now. So what we are doing, we are getting a lot of advice from experts. So we have a lot of partners. Some of them, Vincent will explain later. Some of them giving us, money. Some of them software. But what is for me as technical person very important is external advice. So, for example, having advice from professors that have knowledge in injection, or from turbopumps. We have a cooperation with a Swiss company that are building turbopumps, and they help us. And then here on the right side, you can see a very ancient document. That's also what we are reading. We are really soaking it up. So there's a lot of literature available. Also, Tom Luca mentioned it, the old Russian sketches. So for sure, we are having a look at those NASA documents, old German documents. There's actually a lot available to really read into. And then on the other side, there are some open source projects where we also find our stuff. And I'll show you now a little example of external advice. So here you can see one of our injectors. So this was really one of the first injector designs that we have. So those that you saw prior in the injector plate. So maybe to give a small explanation, you see here on the top, you see here those small holes. Here the LNG is flowing in and then getting swirled because it's like slightly open. You can see it maybe here, yeah. And on the lower section, the oxygen comes from the right side directly after it cooled the engine. So the idea was to do it like that, and then we showed it to a professor, and he said, "Oh, I wouldn't do it like that. Please change it. It's not working. The parameters are too hard to maintain." And that's actually what he suggested us. So at the end, if you see it, in my view, it looks very simple now, and it has a specific reason why he told us that. So I'll show you now. So here you can see one of our results of the first simulation, simulating an ANSYS here. And here I think the swirl gets a little bit clearer how it will behave. But at the beginning, the issue was also always the point where both fluids are colliding. So he told us, hey, you need to make sure that when LNG and the oxidizer are colliding, they should have the same velocity. So he recommended us the design I just showed you. And yeah, that was the result. It looks quite funny, I think. Here you can see the inside, the LNG flowing through the holes, and then, when it collides, it's coming very close. So we still have some work to do to get it at the same point, that it happens at the same point. Yeah, that just to give you a small overview what we are doing right now in the tech team.
Adrian, the simulation looks good, but does this also work in the real world?
Tobias, I don't know. What do you think?
Oh man, you put me on the spot. That's crazy that you asked this. I need this. So actually, we know from previous projects, and I'm sure you know it too. You've worked on any project where you started something in CAD and simulations. It looks amazing. It looks like everything works out. And then you do something in reality, and maybe it explodes. Maybe something goes wrong. But I think this is something that has to happen because, well, you can only get real data on experimenting in the real world. A simulation always just goes this far. And the same is also for risks. So when something goes wrong, it's a risk for parts, for capital, but most importantly, for humans. There's no way, like, once you harm someone, the project is basically done. So one of my jobs is to make sure that everything works well. So there's a topic of risk management. And the thing is, every useful technical system has a risk to it. Take any system, take your car, the car maybe you drove here with, the car you use on a daily basis. You can park it in a garage, then it probably won't kill someone, but the car wasn't built to stand in a garage. It was built to go around for mobility. So it's a matter of risk minimizing. And I want to show you an example where this didn't go too well, and it just happened 5 days ago in China. I have a video for you. Maybe some of you know this. This was supposed to be a static fire. For those of you that are not in the rocket industry, static fire, static, stationary means you don't launch a rocket, like it's happening here, but you just clamp it tight and you fire it to test the engine, maybe the thrust. So this just happened 5 days ago. It went quite viral, I think mainly on X. And it fell down very close to inhabited area. So this is something that here would be totally unacceptable. We don't have things like this happen here. It would be a major disaster, be on every national news. So the question for us, of course, is there are always risks. How to prevent it? Because we can't have things blowing up in Garching. I think Professor Hoffmann wouldn't be too happy about that. The buildings are all still quite new. So we have quality management, also one of my fields of work that I do in the team, which means, well, are the parts that we manufacture like we said they're going to be in the simulation? We have material properties. If the simulation says, hey, this material needs to withstand 200 degrees, well, does it in reality also withstand that? This is one part.
I hope so.
I hope so too. We will have big problems if not. Then we have a part of iterative validation, which I will explain to you just in a minute, of how we start, how to figure out how much fuel do we need, what are the size of the engine. We haven't built a rocket before. How to start it, how to get the first values. And at the end, I have another small piece about safety procedures. So we want to build a rocket. We have a dream. And we have the ability to do some stuff in CAD. But it's not supposed to be useless. We actually want to start somewhere. So what we do is we learn from all the billions of R&D budget that was spent years before us. So in the 1940s, 50s, 60s, different countries spent billions on research. And we are basically using the results of that to use initial values. So we see, hey, what did they do? Can we apply this? And just take that at a base set. We say, OK, we now say we need 28 kilonewtons for our engine to reach the height that we want to reach. Then we look at norms. We look at formulas and plug in the values that we just assumed. And maybe we figure out, oh, the formula now says we need 29 kilonewtons. So we adjust the value. This is like an iterative process that converges ideally. And once we have fixed values, we throw some compute at it. This is where the NVIDIA stock goes up. And we do simulations with it. Sometimes they take a long while, but ideally you get examples like with the injector that Adrian showed us. And then at the end, once we are quite certain that things won't blow up, or at least just behind a barrier that we built, we can do testing. And this is what I'm looking forward most to, because we can create great media, some nice photos, and this is the part where we gain the most knowledge. Now, for all this to be successful, we need quality, which is a really large term. I think there are as many definitions for quality as there are people that try to define quality. So I looked up the slides or the sentences that I learned in my quality management lecture, which I had 1 year ago from my professor. And he had this great German sentence that you surely have to read multiple times to understand from the dean. And it basically says, well, quality is the coherence of a part to its requirements. So you're all sitting on a chair, and Well, let's say we wanted to hold 200 kilos. Yeah? No offense. We wanted to hold 200 kilos. If it holds 250, it's good quality. So we have a requirement, and it adheres to that requirement. That's basically what I learned in university. And now I'm making a small detour, because in Germany we have, or we always say we have a high quality standard. So I prepared this slide, very, maybe offensive to some. Maybe before I say anything, who here drives a Tesla? Anyone? One, two, just two, not that many. Anyone works at Tesla? Okay, then I'm good. Then I can I can roast Tesla. That's perfect. Because I want to tell you a story about quality, and then circle back to what our understanding is of what quality means to us and how the components are used to build. Like, how are we going to build components? Our approach to quality management is something of Tesla do some great things. They iterate fast. They make a lot of progress really fast. And at some points, they say, OK, it's fine if things are not perfect, as long as they work. And in Germany, we have an approach of, hey, we simulate everything to the last detail, we perfect it, and then we build it. Then we have a great product. What we try to do is combine it somewhere in the middle. We studied all in Germany. We like the norms. And
we love them.
We like this approach of doing everything perfect. We want to create a great product. But we can only do our timeline if we work fast. So we say, it's fine if something blows up, as long as we gather data, and before that no one gets hurt. So our expectation is, we gather data, we have a great test, that's our requirement, and if the engine blows up, it was a great test, so still we got the results that we wanted. So to summarize, our quality management, #1 priority, safety. We have a human there with a helmet and a nice safety vest, so we're not going to build rockets like this, even though you might see us on public events dressed nicely. Performance, we have an ambitious goal, so of course we have to optimize parts and think a lot about quality and pushing the last bit out of the material properties. We are working with very small safety margins. And last thing, ideally this all combines that we get success in every mission, as we define it in terms of gathering data. This is how we try to approach our project, but with that, not everything is done yet. We, first of all, need to get resources for it. How do we do that? And also, we have a vision for the future, and that is what Vincent is going to tell you about.
Really cool. Thank you so much, Toby. So maybe a question you guys have been asking yourself for the whole talk. Why are we doing all of this exactly? And it is because we have a long-term goal. We have a long-term vision which we want to pursue within Elara Aerospace. And this is Project Starbound. What you can see here is an orbital rocket. This rocket is able to reach heights of around 500 to 600 kilometers. So basically where most of the major satellite constellations are located at. At the moment, we are actually in talks with various satellite manufacturers analyzing the demand there is. So in the end, we don't just want to establish ourselves as a student team here in Munich, but in the long term, if the demand is there, we could also imagine ourselves really establishing ourselves in the market there. So what I like so much about this construct within Elara Aerospace is that the small rocket we are building right now is setting the cornerstone of the bigger rocket, which we want to build a few years down the road. So maybe let's take this rocket engine as an example. Adrian, you showed it like 20 minutes ago. This is the exact same rocket engine we use in the smaller rocket. For the bigger rocket, it's the same, but it's just multiplied by 9 times. So you can see both projects are relying on one another because we take the learnings from the smaller rocket, can use them in the bigger project, and of course, take the technology with us. So with that rocket, we imagine flying to around the lower Earth orbit and take around 300 kilograms of payload to there. So there's a lot of room for some smaller microsatellites, which we can put to space. So for all the sponsors, we want to create a win-win situation. What we can give in return to all those sponsors is publicity. We're talking about the logo on the rocket. We are talking about the logo on the website, common social media posts we do, case studies we do together, but also pretty odd things you wouldn't think about at first. I remember with Formlabs, we attended the Form Next in November of last year. It's an additive manufacturing conference where we displayed parts, 3D printed parts that Formlabs created for us, and yeah, further boosted some publicity and ours and their projects as well. So in the end, we want to really create a win-win situation for all the partners and of course, keep our sponsors happy. You might ask yourself, how do we get those sponsors? That's a really good question, and there's mainly two ways. There's contacts and events. Contacts. What you can see here is a meeting with Mr. Hoffmann we had a few months ago. Mr. Hoffmann is the president of the Technical University of Munich, and the cool thing about him is he is a multiplier. He knows so many people, he has so many people in his network, and I mean, he's in touch with the most DAX concerns, with also the C-levels in there. So whenever we need something, we know who to reach out to and get some warm leads from him, get some intros. And this is why a collaboration with Mr. Hoffmann and Tum especially is very, very valuable to us. And next up, we have events. So what you can see here is a picture we took at the Munich Management Colloquium. This was back in March, was a huge conference with many different sponsors. We also acquired there for, let's take Acceleron as an example. They're a sub-company of ABB, was in the future in the
ABB2.
Exactly, ABB Tuber Systems. So we talked to the CEO there. He liked the project. He invited us to his office in Switzerland. I think it was near Zurich, right?
In Baden. It was in Baden.
Baden, yeah. But in Baden.
No, only Baden. Once Baden.
Really cool, once Baden. So we had a great meeting with them, and now they're also backing us with some financial amount for that project. So really, really cool to see what can happen out of events like this. So we're really, really happy to chat with you afterwards as well. If there's someone interested in supporting us on that project and make history together, we're really glad to talk to you later. So what you can see there as well is a half-scale prototype of our rocket. So we said it before, the big one is going to be 10.5 meters. This one was a 5-meter prototype. We also have that displayed here today at the big Techday. It's just in the other building in the Motor World at the first floor. So if you want to take a look at it, if you want to talk to us later, this is exactly where we are. And when talking about events, I said it before, we want to have a huge event at our launch site. So we want to have a lot of people on there. We want to have family and friends. We want to have our biggest sponsors there as well. And if anyone is interested in coming to the launch in Sardinia, if you have your holiday planned for end of Q2 next year in Sardinia, then feel free to come around, because I often hear that when I talk to friends that they have that on their bucket list, you know, things they want to do in their life, that they really want to see a rocket launch with their own eyes, because it's just a different kind of experience. So we're also open to that, and yeah, I'm looking forward to talking to all of you later. And with that, see you in Sardinia.
Very cool. Thank you, guys, for this amazing talk. And I think with that, we can start the Q&A section. So are there questions? It starts at the front, so we can start here.
Very interesting talk, first of all. Thank you. I have a rather technical question to begin with. Yeah. You talked a lot about the rocket and also the launch provider in Sardinia.
Yeah.
Yeah. How does it work that those two fit together? So, I mean, big rocket companies build their own launch towers. They fit this hardware really tight together. How does it work with a provider? Do they have like specs? Here, tank, please? Or how does it work?
Test, it works again. Okay. So it works like that. So OLM is building a suborbital launch site and an orbital launch site. Since in the first launch, the rocket you see here, it's really suborbital. So they are setting a suborbital launch site. And in this case, for us, we are, for example, cooperating with them, building a flame diverter. So we will ourselves build the mount. I think that's where you're referring to. And then put it on top onto their flame diverter. So we are having meetings with them weekly where we discuss how to approach that. For other rocket companies, I think it's, as you mentioned, difficult because the systems are quite different. So for the bigger ones, it will be very different, and I think it's very individual, actually. Yeah.
I mean, right now we're at a smaller scale, so this works out perfectly fine. Yeah.
Thanks.
Thank you. Further questions over here?
Yeah, circling around back to the beginning, you mentioned a soft splashdown in the ocean, and then see if you can refurbish it. Isn't saltwater corrosion usually a big problem for rocket engines?
Yeah, so salt water is one of the problems that we are aware. So the design will have, or the goal is to retrieve the rocket as fast as possible after splashdown and then desalt it on site. So we will do the desalting on site on Sardinia just after we reach the port again. And then we have to see what the damage is actually to the rocket. So we'll probably have to redo all the screws, disassemble the rocket engine and take it apart to its core components. But we do hope that we can refurbish those parts and with a bit of cleaning, get them running again for a second static fire and for another launch.
Yeah, thank you. And also thanks for the nice talk.
I think, just if I might add something, I think it's similar to many other parts where we will figure it out once it's splashed down, how much it can be reused. We've never done it. We will see, but the good thing is we're gathering real-world data. Yeah.
Okay, thank you.
There's questions in the back.
Question at the back? Or more questions at the back? I will go a bit here, then I'll move around a bit.
Hi, my question is, you showed us that you use oxygen for the regenerative cooling, and my question is, why did you decide for oxygen instead of methane for that cooling?
It's a good question. Actually, we were deciding on that because the oxygen is slightly cooler, so we have a better cooling effect. But in the beginning, it was changed up. So the slides I showed afterwards with the injector, in the first one on the left side, you saw before it was the other way around. And then we decided against it after we got the advice from the professor that said, hey, make sure that both fluids collide with the same velocity. And then it was a matter of that first cooling, and on the other side also to prevent the risk of a hard start. So having a hard start, I don't know if you're familiar with that, would mean that you have an explosion inside there and that would blow up the whole engine. So that were a mix of those reasons for that.
I think Tom Luca.
Yeah. One more addition, we will be doing an engine chill down before operation, and if we have liquid methane running through the cooling pipes and that vaporizing or turning into a gas, it will be an issue. So oxygen will not be that much of a problem once it comes to the chill down process.
Thank you. Next question.
Yeah, thank you for the great talk. And my question would be, what is the probability of the rocket exploding at the start? I mean, you test a lot of the parts individually, but this is a whole system working together.
So before the first launch, we will do a big integration test. So we will do a static fire of the engine itself, hopefully here in Germany. After that, once we are on Sardinia, we will do wet dress rehearsal and possibly a static fire of the entire system before we do the launch. And after the first static fire on the launch pad, actually, we will do the launch if all the data is good. So we'll try and mitigate the risk as much as possible.
Thank you.
All right. Next questions over here. Okay.
Thank you for the talk. My question is, what are the legal implications of doing an engine test in Germany? Because you said launching the rocket, the legal implications are done by the provider, but for engine tests it's different, right?
So launching or testing a rocket engine in Germany is quite difficult. So there are some places where they are actively testing rocket engines. But if we don't get the regulatory approval for Germany, we do have the option of testing our engine on the launch site in Sardinia. So we do have backup options if the legal issues become an issue, actually.
Yeah, so this is something we are in close contact with our partners with, because in the end, they have done that before and they know how to do it. And this is why we have several options on where to do the test and with whom.
So no engine testing in Garching then?
No, in Garching there's a possibility of testing engines, but not at this size, actually, right now. So maybe as an example, we know from RFA that they are testing their engine in Augsburg, and they have really issues with the neighbors because it's really loud. So that's that's one of the issues. We'll see if we manage it in Germany.
Thank you.
All right, next.
There's also someone in the front.
At the front, let's go back to the front.
Like
you guys let me run around a lot.
Okay, thanks for the great talk. I actually have a question out of technical curiosity, because you mentioned that you don't use like a gas turbine to pump the gases into the chamber, but you use an electric pump. So now that we know that about the 1 ton rocket has about 700 kilograms of fuel, how much of that is also the battery that you need to carry for this?
That's a good question. The reason why it works out is that the engine will be only propelling for around 76 seconds. So the weight of the battery will be around 50 kilo. So it could be worse, but for sure there's always advantages and disadvantages, and that's the weight.
So will that also scale up the same way for the larger rocket?
Yes, yes. So there are some solutions to that. Maybe if you're familiar with some other rocket companies, so they throw away their batteries at a later state to reduce to reduce weight. But for the small rockets that we're building now, this is not planned.
Okay, thank you.
Yeah, you're welcome.
All right, the last question, I would say. You're lucky.
Is the rocket you're building right now, does it have any use cases to just fly into the 100 kilometers, or is it just a test rocket?
Kind of both. So for us, it's to validate all systems, so rocket engine, airframe, all the constructions. But there are tests that DLR is doing also with sounding rockets, where they take student experiments to 300 kilometers altitude for students then to run those tests. Some students have tested heat shield materials and testing those on re-entry of the subalto rockets, but there are many more experiments that actually do have a use case. Pharmaceutical companies, they also do a lot of experiments in subalto space and then return the capsule. Some experiments can be done in a couple of seconds. That's where we would be able to offer as well a bit of payload area for those companies.
Very interesting, thank you.
All right, and with that, I think it is time for us to thank our experts here. It was a great talk.
Thank you so much.
And we also have a few presents. I think if there are further questions later on, you can find those guys on site.
Exactly.
Thank you.
Thank you so much.